and probability measuring ML2, you just square the corresponding Klebs-Gordan coefficients, which is very nice. So as long as you know what those coefficients are, you can find the probabilities easily. But the downside is calculating those coefficients, the Klebs-Gordan coefficients in the first place, because you probably remember from the previous session or two how tedious it was. Right? It was difficult. So in practice, for working theoretical physicists, there are tables, published tables of CG, Klebs, German word, I guess, Klebs-Gordan coefficients. So these tables, you can look them up in in appendices of serious quantum mechanics graduate level textbooks and so forth. Okay, so they're provided, and once you have them, you can just use them, find the appropriate ones in the expansion that you're talking about, for a given value of L and S and all that sort of thing. Find the appropriate table, look at the appropriate item in the table, and square it, and that'll give you the probability that you're looking for. Right? Okay, and saves a lot of work by using tables. All right, 2 lines, sort of a new thought. Now, I've mentioned the idea that angular momenta of 2 kinds, orbital angular momenta symbolized by L, and spin angular momenta symbolized by S. Those 2 can interact. Both of them have a magnetic moment. Like if you have, in a sense, well, using a classical crude analogy, like the charge inside an electron. That's crude, but the electron has a magnetic moment. It's though as if this internal charge in the electron sort of spinning around, so you have a kind of charge, a loop of charge moving around. So that creates a kind of little magnet in effect. If you have a looping charge spinning around, that generates a kind of magnet, little magnet. So the electron has a magnetic moment, and that's from a spin, and it's looping around the nucleus as well. So there's an orbital angular momentum, and so there's a magnetic moment due to that as well. And you get a kind of, well, from the point of view of the electron, I'm anticipating the next session, so perhaps I should wait then. But in brief, there's a kind of interaction that can occur due to the magnetic moment of orbital angular momentum and the magnetic moment of spin angular momentum. And that interaction, like one generating a force on the other in a sense, is usually just called spin-orbit interaction. And it creates potential energy, which you add to the Hamiltonian, and then you can make corrections to the eigenvalues to the Hamiltonian, because after all the Hamiltonian is just the energy operator. Remember, go quite a few lectures back for that idea. So you can add this extra potential energy due to the spin-orbit interaction, and that will give you corrections, slight modifications, delta E, small change in the energy eigenvalues to your Hamiltonian, and we'll do that in the next few sessions. Okay. Now so both the the electron has a spin magnetic moment, and it's going around the nucleus, so it has an orbital magnetic moment. And so you'll see next sessions. So if we take the case of an electron where the spin is +1/2 and its orbital angular momentum L is non-zero, okay? So under those circumstances you get a spin orbit interaction. Now, if that's occurring, if you put the atom in a magnetic field, then the J, in effect, and remember J hat equals, in this case, L hat plus S hat. That J, think of it as a vector if you like, and imagine the magnetic field direction is just vertical, then that J will precess like this around that the orientation of the magnetic field. It's sort of analogous in classical mechanics to a spinning top, right? If you pull a string and the top spins like crazy, and you know it's spinning, but its axis of rotation of spinning will precess. And the Earth does this as well, slowly, but you know, its axis, the spinning of the Earth, its axis is also precessing. And the precession period is, I don't know enough astronomy. Is it thousands of years? I better plead ignorance. But the Earth also precesses, and so I'm not sure if it's the electron or the atom. Anyway, this J precesses, so it does this sort of thing about the orientation of the magnetic field B as a thing. B is a vector. Okay, so it'll do this around this B, the magnetic field strength vector. Okay. Now, a comment here in the text is that this J, J hat, which is L hat plus S hat, think of that L hat and S hat as not independent. They're not these two things. They're not precessing independently. It's as though the J, they're linked, and as the J is that precesses. And this linkage, this spin-orbit interaction, another name for it is, I guess the people who thought about it originally, the Russell and Saunders, sound like two English names, perhaps American, but native English names, I guess. So spin orbit interaction, or Russell-Saunders coupling. Okay, and it's valid. It's valid for the lighter atoms, where the velocity of the electron is much less than, the symbol, a lot less than c. C is the speed of light. It's the famous C as in E equals mc squared, mass times the square of the speed of light. Okay. Now, I don't know if you can see it. Well, next line. We're dealing in sessions like this, you get cut off in mid-sentence. So, when you have a heavier atom, so that means more protons in the nucleus, so a stronger force on the electron, because greater attraction, Coulomb attraction, and so there's more energy involved. The speeds of the electrons increase and hence get close to the speed of light. So this type of coupling it becomes, in numerical terms, relatively less important. So this coupling's readily observable for lighter atoms, where you don't get this sort of relativistic effect, where the speed of the electrons is so high, close to the speed of light. But for light elements, the speed of the electrons is less, and hence the energies concerned are less, and hence these small changes in the energy eigenvalues of the Hamiltonian are more noticeable. And we'll talk about these energy corrections in later sessions. Right, so I'll stop there.